So let's see. Well, on the Starship front, we've gone through many iterations, starting from not really knowing how to build rockets at all with Falcon 1, and having 4 failures actually in reaching orbit. Three failures, and then the fourth one got to orbit. So fourth one's a charm. So we only barely survived. I was at zero cash basically when we got that fourth one to orbit, and if that fourth one hadn't worked, we would have been curtains. So it's definitely not been smooth sailing. It's been a very difficult ride, with just a lot that has been discovered along the way. Just trying to figure out what questions to ask about the design was quite difficult. I think it's helpful to have as the objective the creation of a self-sustaining city on Mars. I think this has to be the objective, not simply a few people or a base, but a self-sustaining city. The acid test really is if the ships from Earth stop coming for any reason, does Mars die out? For any reason. It could be banal, or it could be nuclear Armageddon. Doesn't matter. If the ships stop coming for any reason, does the city on Mars die out? If it does, we're not in a secure place. So, I mean, I think this really might come down to, on the Great Filter front, are we going to create a self-sustaining city on Mars before or after World War III? And I think the probability of it being created after World War III, hopefully there's never a World War III, but of after is low. So we should try to make the city self-sustaining before any possible World War III. This is just a risk. This is not, I think sometimes people have difficulty dealing with probability to see that this way or that way, but it's really, we just face a series of probabilities. And there's some chance that we will have a giant war or a super volcano, or a comet might hit the Earth, or we might just self-extinguish in some. It might be more of a whimper than a bang. And frankly, right now, civilization is not looking super strong. It's just looking a little rickety right now, to be frank. I mean, unless Mars is made self-sustaining, which will probably not happen in my lifetime. It is certainly not. It's meaningless to have an escape, lifeboat or escape hatch or something if you're simply moving to another place where you will soon die out. That doesn't count. It's not much of a lifeboat, really. So this is really about, minimizing existential risk for civilization as a whole, and then having an exciting future that you can look forward to, and a future where we are a spacefaring civilization and multi-planet species is far more exciting than one where we are not. That's an exciting future, and being forever confined to Earth until some eventual extinction event is depressing and not fun. And we need things that make you want to get out of bed in the morning and be excited about the future. And I think being a spacefaring civilization is one of those things that everyone can get excited about.
But can you maybe just kind of lead people along the path that led you from the design from Falcon 9 to Falcon Heavy, but now Starship is rather different than Falcon Heavy.
Yes.
The engineering.
Absolutely. Absolutely. I didn't quite answer your original question. You first have to say what is the goal. And once you have what is the goal, you can then measure the various designs against that goal. Otherwise, you're saying, how are you evaluating why is one design better than another? What's your goal? It's got to be a goal. So the goal is get enough tonnage to Mars and enough people to make Mars self-sustaining as quickly as possible. So then you say, okay, let's back out the math on this. We're going to need a lot of tonnage. Maybe, I don't know, 100,000 tons, maybe 1 million tons. So you can't be faffing around with these expandable rockets. They're a joke. They're absurd. Even Saturn V is tiny potatoes. we need it, because if you want to get, like, let's say first order approximation, 1 million tons to the surface of Mars, inclusive of people, that means probably something around 4 or 5 million useful tons of payload into a low Earth orbit. For every ton you get to low Earth orbit, you're going to get 4 or 5 tons, hopefully closer to 5. This math is, you really start squeezing like tiny percentages. But let's say confidently, if you got 5 tons to low Earth orbit, you can get 1 ton to Mars. That's confident. Maybe you can get, maybe you only need 4. Anyway, the point is, you need 5 million tons into Earth orbit to get 1 million tons to Mars. Now, let's put this into perspective. Total global capacity to orbit of all expendable rockets is around 500 or 600 tons, I think. And if you said, okay, the world's going to end if you do not increase your capacity, perhaps they could do 1,000 tons. Okay, so that's 1/5000th of what's needed. This is ridiculous. It's not even, 0.1% would be, 1,000th. So way less than 0.1%. We have way less than 0.1% of the capability needed to create if everyone went full tilt with expendable rockets. Expendable rockets are just utterly stupid, in my opinion. Utterly stupid. They're a complete waste of time. People should stop wasting their time. If you try to sell an expendable plane, people would laugh you out of the room. If you try to sell an expendable car, they would laugh you out of the room. If you try to sell an expendable horse, they would laugh you out of the room and think there's something wrong with you mentally. So all of these things are reusable. It's essential to be reusable. Now, creating a reusable rocket, orbital rocket, is very difficult. Doing a suborbital reusable rocket is easy. Doing a reusable orbital rocket is hard. Even when a lot of smart people have put quite a bit of effort into it, they might get 2 or 3% of the lift-off mass to low Earth orbit. And a really epic rocket would get 4. I'm not sure, I don't think anyone's ever gotten 4. But you basically need to have something that in expendable form would probably get about 4% of its payload to orbit, such that you can spend about half of that 4% on reusability and still net out to around 2% of payload to orbit. So you have to make both the booster and the upper stage and the fairing, everything reusable. With Falcon 9, so with Falcon 1, we did actually attempt to do this. So we had a parachute from the first stage, but really did not appreciate that first stage was going to hit the atmosphere like a concrete wall. So at first I got pretty mad at the parachute supplier until I realized, it's not their fault. We were just big fools. That thing was exploding as soon as it hit the atmosphere. So you really got to do something to ease the transition into the atmosphere at high Mach number. It's very hot, and there's a lot of force and a lot of heat. So then with Falcon 9, we made a bigger rocket, and our scale matters here because you do get basically economies of scale. You can't have a tiny rocket. There's a tiny rocket, you basically just end up carrying your electronics to orbit. So your avionics, So in a little rocket, if you're small enough, just your avionics alone ends up being a significant percentage of your payload, and then you end up, if you had a rocket that was, I don't know, trying to get a 10,000 pound rocket, for example, or even a 10,000 kilogram rocket to orbit, I think you would basically get 0 payload. Now, as you get bigger, the rocket gets bigger, but the brain doesn't get bigger. The brain can stay the same size. So your avionics, for example, become almost 0% of the weight for a big rocket. Then for big rockets, you also get gauge advantages. So we're really in the nuances of rocket design and manufacturing here. If things are very small, it's difficult to get your gauge accurate. So basically, how thick is the material? Like you want to do castings, For example, there's a minimum gauge or thickness for a casting. There's a minimum kind of error bar on the on the material skins. Even for a composite rocket, you've got you start hitting granularity issues. As you get bigger, you're no longer gauge limited, and you can get your percentage accuracy on the thickness of walls and castings can be very good. These are nuances that I think almost no one appreciates, but suffice to say that there are advantages to size. And you can certainly see this in many walks of life where if you've got a truck that's carrying cargo, it's more efficient to have a big semi-truck, not a bunch of little trucks. For ships, it would be pretty silly to see container ships or containers going across the ocean one at a time with little outboard motors. That would be silly. You put them on a container ship. You have big ships, not little tiny ships. So anyway, so size matters, it really does. And full reusability matters. So with Falcon 9, after immense effort, we were able to achieve reusability of the booster. And we're mostly achieving reusability at this point with the fairing as well. But this is a monumental effort. And I think within its architecture, Falcon 9 is close to a local maximum. If you say, gas generator cycle, kerosene, oxygen vehicle of this particular size with a 12-foot or 3.6 meter diameter, which is that size because of road transport limitations. So if you go bigger than that, you can't transport it over the road, and your logistics costs become extreme. But having a long, thin rocket is not very mass efficient. You end up having to have thicker skins to take out the bending moment. And then having, like, kerosene is not the right fuel. Methane is a much better fuel. You can get higher ISP. A specific impulse, basically efficiency. I mean, for those who, I think probably a lot of those who are listening know what the rocket equation is, but in simple terms, it's very simple. It's like a rocket is going to go further if it shoots the gas out of the end faster, and if a bigger percentage of its mass is propellant. It's obvious. So that's what the rocket equation says. So shoot gas out faster in the right direction and increase the propellant, the percentage of propellant, that's going to get you go further. With methane, you can shoot it out faster. and
you can make it on Mars.
You can make it on Mars, for sure. Exactly. So being able to do in-situ propellant development or production is very important. So you don't have to carry your return fuel with you, or return fuel and oxygen. Rockets are mostly oxygen or oxidizer. So, and there's some other subtle advantages with a oxygen methane system in that you can go to a higher percentage, a higher mass ratio of oxygen. So with kerosene, you'd be at about roughly 2.5 to 1 oxygen to fuel mass ratio. With methane, you're more like 3.5 to 1. And you actually want that higher mass ratio because oxygen is very dense and it's inexpensive, especially on Earth. So you're gonna, you have all these plants just making oxygen all day long, and plankton just making oxygen, never do anything. So the cost of oxygen is basically the cost of electricity. Anyway, so going from Falcon, going from kerosene, which is basically the same as jet fuel. It's like RP1, rocket propellant grade kerosene, is just a tighter grade of jet fuel. You want to go from that to something where the gas shoots out faster, and that's methane, and where in-situ production of propellant is easier. So that's why the change from kerosene to methane. Methane is just CH4. It's 1 carbon, 4 hydrogens, and then the oxygen pairs together. So you have it's called O2 because oxygen pair bonds. And obviously, you know all this stuff. Well, it's not like we're obviously venturing into unknown territory. So it's not as though I have all these secret dates and I'm just keeping them from people. But these are just guesses, obviously. I'd say I'm 80 to 90% confident that we will reach orbit with Starship next year. I think probably 50% confident that we'll be able to bring the ship and booster back. That's more of a dicey situation. We'll probably lose a few ships before we really get the atmospheric return and landing right. We might lose. Hopefully, we don't lose it. Hopefully, we don't lose any boosters because that's a lot of engines. Our initial booster flights will just have maybe 2 to 4 engines, not 28. 28 is a lot of engines. So, and then I think we'll probably be in doing high volume flights. I think probably in 2022, so a couple years from now. But I'm trying to make sure that our rate of innovation increases. It does not decrease. This is really essential. In fact, if we do not see something close to an exponential improvement in our rate of innovation, we will not reach Mars. Like a pure linear doesn't get there. Well, I'll be dead anyway before it gets there if it's pure linear. If it's exponential, I think we could get to Mars. We could probably send an uncrewed mission there in maybe 4 years. There's a Mars conjunction every 26 months. There's one this year, so that means in a couple of years from now there's another one, and then 4 years from now there's another one. I think we've got a fighting chance of making that second Mars transfer window. No. We're focused on, like I said, it is important to have the objective be right. That's why I was talking so much about the importance of making Mars building a self-sustaining city on Mars. If that's the objective, then obviously, just putting some satellites in orbit that's not important. You have to achieve full and rapid reusability. I emphasize full and rapid. Reusability is only relevant to the degree it's rapid and complete. And then you also have to do orbital refilling. This is essential as well. And then propellant production on Mars, also essential. So, with that as the goal, then that means that creates, I think, a good forcing function for radical innovation, because in the absence of radical innovation, we have no chance of meeting that goal. Whereas if our goal is simply, defeat Lockheed and Boeing or something like that, that we would probably achieve that goal.
You've already done it.
That really wasn't even a thing, Yeah. I wish it was. They're not really trying to do, not even trying to do reusability, which is bizarre because they make planes that are reusable. So, I mean, if they talk to if they talk to one of their customers, buys a Lockheed fighter jet or a Boeing aircraft, like, hey, we're going to sell you a 737 that can be used once, and it's not the 737 MAX. But that turns out that was a single-use airplane at times. But it really. It would be an absurd thing for them to sell a single-use aircraft, but they feel quite comfortable selling a single-use rocket. Anyway, but if our goal is simply we're going to be the leaders in launching the conventional satellites that exist, we would probably approach that on a sort of a logarithmic basis, where you'd get there and you sort of slowly make progress towards doing 10 launches a year, 12 launches a year, while they do 6 or something like that. I don't know. But since the goal is, hey, we need to make life multiplanetary before it's too late, and time really matters, so it's like we're shooting for Mars, not just the moon. It's not let's shoot for the moon, shoot for Mars. And then these competitive things are kind of small things along the way. Unless somebody else is shooting for Mars, they will not be competitive with something as pedestrian as launching a few satellites into Earth orbit.
So how can the Mars Society help you?
Well, I do think there's, in order for there to be a self-sustaining city on Mars, we're going to need an intersection of sets here. One set is the set of people that want to go and can either find sponsorship, they can either afford it themselves or find government sponsorship or take out a loan or whatever the case may be. But somehow you've got to have the set of people who want to go to Mars and can come up with the funds somehow to do that. And then I should say there's two sets: desire to go to Mars and can afford to go to Mars. When desire to go to the people who want to go to Mars and the people who could afford to go to Mars, when that intersection of sets reaches 1 million roughly, then I think we will have this city on Mars.